In previous lecture videos, we derived characteristics of the sampling distributions of the least square estimators of the beta parameters in the simple linear regression model. Using the means and the standard deviations of these sampling distributions, we looked at two ways of approximating probabilities of events involving the least squares estimators. The first approach we looked at was based on Chebyshev's inequality. This approach gives bounds on probabilities that are guaranteed to hold, and it is applicable in any situation in which the standard deviations of the sampling distributions of the estimators are finite. But because this approach is so broadly applicable, and because the bounds it gives are guaranteed, the bounds are very, very conservative in most cases. And when more information is available about the sampling distributions, for example, their shapes, better approximations can often be found. We then looked at approximating probabilities using the empirical rule. This approach gives more accurate approximations than Chebyshev's inequality when the sampling distribution of the least squares estimator is bell-shaped. Well, this raises the question, under what conditions will the sampling distributions of the least squares estimators be bell-shaped? In this lecture, we begin looking at this question and provide sufficient conditions for the sampling distributions of the least squares estimators to be bell-shaped, and more specifically, normally distributed. This will be the case when the model error terms are themselves normally distributed. So here's an outline of the topics we'll be looking at in this lecture. We'll first look at the sampling distribution of beta 1 hat. We'll identify the sampling distribution of beta 1 hat when the model error terms are normally distributed. We'll then provide the functional form of the PDF of the marginal distribution of beta 1 hat in this situation. We'll then identify the sampling distribution of the standardized version of beta 1 hat. And then we'll look at how to calculate probabilities involving beta 1 hat in this situation. We'll then look at the sampling distribution of beta 0 hat. We'll identify the sampling distribution of beta 0 hat when the model error terms are normally distributed. We'll then provide the functional form of the PDF of the marginal distribution of beta 0 hat in this situation. We'll also identify the sampling distribution of the standardized version of beta 0 hat. And finally, we'll look at calculating probabilities involving beta 0 hat in this context. We'll then identify the joint sampling distribution of beta 0 hat and beta 1 hat. We'll identify the mean vector of the joint distribution. We'll then specify the form of the covariance matrix of the joint distribution of beta 0 hat and beta 1 hat. We'll also specify the form of the correlation matrix for this joint distribution. And finally, we'll provide the functional form of the PDF of the joint distribution of beta 0 hat and beta 1 hat. So let's start by looking at the sampling distribution of beta 1 hat. We have shown that the mean of the sampling distribution of beta 1 hat is equal to beta 1 itself, and that the variance of the sampling distribution of beta 1 hat is given by sigma squared over S sub xx, the variance of the model error terms divided by the corrected sum of squares of the x values. We have also seen that beta 1 hat can be written as a linear combination of the responses y1, y2, and so forth up to y sub n. One of the standard assumptions about the model in regression analysis is that the error terms are normally distributed. When this is the case, by corollary 1.4.3, the response variables are normally distributed as well. Since beta 1 hat is a linear combination of the responses, then also by corollary 1.4.3, it follows that the least squares estimator, beta 1 hat, is normally distributed itself. Putting all of these results together, if the standard assumptions about the model error terms, epsilon 1, epsilon 2, and so forth up to epsilon sub n, in the simple linear regression model are true, that is, that they are mutually stochastically independent and normally distributed, all possessing the same variance, sigma squared, then beta 1 hat is itself normally distributed, and the mean of its sampling distribution is beta 1, and the variance of its sampling distribution is sigma squared over S sub xx. With this information, we can actually find the functional form of the PDF of the marginal distribution of beta 1 hat. Denote by F sub beta 1 hat the probability density function, or PDF, of the sampling distribution of the least squares estimator beta 1 hat. Since under the current conditions being considered, beta 1 hat is normally distributed with a mean of beta 1 and a variance of sigma squared over S sub xx, it follows that the PDF of the sampling distribution of beta 1 hat is that of a normal distribution with mean equal to beta 1 and variance equal to sigma squared over S sub xx. And that PDF is given at the bottom of this slide. Next, let's find the sampling distribution of the standardized version of beta 1 hat. Denote by Z sub beta 1 hat the standardized version of beta 1 hat. That is, Z sub beta 1 hat is equal to beta 1 hat minus the mean of its sampling distribution, which is beta 1, divided by the standard error of that difference. The standard error being the square root of sigma squared over S sub xx. If beta 1 hat is normally distributed, and again if the model error terms are normally distributed, then beta 1 hat will be normally distributed. Then the standardized version Z sub beta 1 hat is also normally distributed, with mean 0 and variance 1. In other words, the standardized version of beta 1 hat, Z sub beta 1 hat, has a standard normal distribution. Next, let's look at the process of finding probabilities of events involving beta 1 hat. When the model error terms are normally distributed, beta 1 hat is also normally distributed. Therefore, probabilities of events involving beta 1 hat can be calculated in the same way that probabilities for any other normally distributed random variable can be calculated. Perhaps the most commonly used approach is to transform a given probability statement that involves a general normal random variable via standardization into an equivalent probability statement involving the standard normal random variable, and then using the standard normal table to look up the appropriate probability. As an alternative, one could use a calculator or computer software that has the normal CDF built in. To denote this process notationally, denote by cap phi the cumulative distribution function, or CDF, of the standard normal distribution, and let Z denote the standard normal random variable. The following slides show this standardization process expressed in terms of beta 1 hat for left-tailed probabilities, right-tailed probabilities, and probabilities over a bounded interval. So let's look first at the process for calculating left-tailed probabilities. And so we want the probability that beta 1 hat is less than or equal to some constant C. Now this first step follows by standardizing both sides of the inequality inside the parentheses. If we do that, then the two events are equivalent, and because the events are equivalent, they have the same probability. The next step follows because we are standardizing beta 1 hat, and the standardized version of beta 1 hat has a standard normal distribution. And so we can replace the standardized version of beta 1 hat by a standard normal random variable. And the last step follows just by the definition of cap phi, the CDF of the standard normal distribution. Next, let's look at the process of calculating right-tailed probabilities involving beta 1 hat. In particular, the probability that beta 1 hat is greater than or equal to some specified constant c. Now first notice in the first step that we have replaced the non-strict inequality greater than or equal to by the strict equality greater than. Now this is justified because for continuous random variables, the probability of a single point is 0. So a single point, actually a discrete set of single points, can be removed from an event without changing its probability. And so by continuity then, the probability that beta 1 hat is greater than or equal to c is equal to the probability that beta 1 hat is strictly greater than c. The next step follows from the complement rule. And so the probability that beta 1 hat is strictly greater than c is equal to 1 minus the probability that beta 1 hat is less than or equal to c. And the last step follows by standardization and the definition of Ph.D. Finally, let's look at the process of calculating probabilities involving beta 1 hat over an interval. And so again, notice first that in the first step, we are replacing the non-strict inequality beta 1 hat greater than or equal to c1 by the strict inequality beta 1 hat strictly greater than c1. And this is justified again by the fact that beta 1 hat, if it's normally distributed, is a continuous random variable. The next step is justified by decomposing the joint probability in the previous statement. And then finally, the last step is justified via standardization and the definition of Ph.D. And so to calculate probabilities involving beta 1 hat, we can use this process of standardization plus the standard normal table to compute these probabilities. And so, for example, here is an example of a standard normal table that you've used in previous courses. We could also use a calculator that has the normal CDF built in. And so, for example, the TI-84 Plus has the normal CDF built into it. And so, for example, if we wanted to calculate the probability that the standard normal random variable is greater than 1.645, we could access the distribution functionality in the calculator by pressing the second and then vars key. That brings us to the distribution menu. The second option is the normal CDF function. To find the probability that z is greater than 1.645, we would enter as the lower endpoint of the interval 1.645. For the upper endpoint, we would enter 1 times 10 to the 99th, which is how it represents infinity. And then since we're dealing with the standard normal random variable, it has a mean of 0 and a standard deviation of 1. We would enter those values into the respective locations as shown on this wizard screen. And then finally, we would press enter, and that would paste the normal CDF function with the arguments we've specified onto the calculator screen. And so it would give us a value of 0.05. All right, next let's look at the sampling distribution of beta 0 hat. The mean of the sampling distribution of beta 0 hat has been shown to be equal to beta 0 itself, and so beta 0 hat is an unbiased estimator of beta 0. The variance of the sampling distribution of beta 0 hat was shown to be sigma squared times the sum of the squared x values divided by and times the corrected sum of squares of the x's. Now we have also seen that beta 0 hat can be written as a linear combination of the responses. If the model error terms are normally distributed, then so are the response variables. And since beta 0 hat is a linear combination of the responses, by corollary 1.4.3, the least squares estimator, beta 0 hat, is also normally distributed, and it has a mean of beta 0 and a variance of, again, sigma squared times the uncorrected sum of the squares of the x's divided by and times the corrected sum of squares of the x's. With that information, we can actually find the functional form of the marginal distribution of beta 0 hat. So denote by f sub beta 0 hat the PDF of the sampling distribution of the least squares estimator, beta 0 hat. Since under the current conditions being considered, beta 0 hat is normally distributed, it follows that the PDF of the sampling distribution of beta 0 hat is that of a normal distribution with mean equal to beta 0 and variance equal to sigma squared times the sum of the squared x values divided by n times s sub xx. And so the PDF shown at the bottom of the slide is the PDF of beta 0 hat. Next, let's look at the sampling distribution of the standardized version of beta 0 hat. Denote by z sub beta 0 hat the standardized version of beta 0 hat, that is, z sub beta 0 hat is equal to beta 0 hat minus the mean of its sampling distribution, which is beta 0, divided by the standard error of that difference. The standard error being the square root of sigma squared times the sum of the squared x's divided by n times s sub xx. Then, if beta 0 hat is normally distributed, the standardized version z sub beta 0 hat will also be normally distributed with a mean of 0 and a standard deviation of 1. In other words, if the model error terms are normally distributed, then beta 0 hat is also normally distributed, and the standardized version of beta 0 hat will have a standard normal distribution. Next, let's look at how to calculate probabilities involving beta 0 hat. And so again, we'll start with left-tailed probabilities. So the probability that beta 0 hat is less than or equal to some specified constant c. And so by standardizing both sides of the inequality within parentheses, we get an equivalent event, and so their probabilities are equivalent. Since the standardized version of beta 0 hat has a standard normal distribution, as we've just seen, we can replace the standardized version of beta 0 hat by a standard normal random variable z. And then the final step is justified by just appealing to the definition of cap phi, which is the CDF of the standard normal distribution. Next, we'll look at right-tailed probabilities involving beta 0 hat. So the probability that beta 0 hat is greater than or equal to c. The first step, again, replacing the non-strict inequality greater than or equal to by the strict inequality greater than, is justified because the normally distributed random variable beta 0 hat is a continuous random variable. The next step is justified by application of the complement rule. And the last step follows by standardization and the definition of cap phi. And then finally, we'll look at probabilities involving beta 0 hat over an interval, over the interval from C1 to C2. So the first step, where we replace the non-strict inequality, beta 0 hat greater than or equal to C1, we replace that by beta 0 hat being strictly greater than C1. Again, that follows or is justified by continuity. The second step is justified by decomposing the previous probability, and then the last step is justified by definition of cap phi. Okay, next let's look at the joint distribution of beta 0 hat and beta 1 hat. we'll first look at the mean vector of the joint distribution. So let bold beta denote the 2x1 vector containing entries beta 0 and beta 1 in the first and second rows respectively. Next, denote by beta hat the 2x1 vector containing the least squares estimators of beta 0 and beta 1 as entries in the first and second rows, as shown here. The mean vector of the joint distribution of beta hat, denoted by mu sub beta hat, which is the same as the expected value of the random vector beta hat, is equal to the 2x1 vector beta. And so it follows that the vector of least squares estimators is an unbiased estimator of the vector of beta parameters. Next, let's look at the covariance matrix of the joint distribution of beta 0 hat and beta 1 hat. Let cap sig sub beta denote the 2x2 covariance matrix associated with the joint distribution of the vector of least squares estimators, beta hat, which again is the 2x1 vector containing the least squares estimators, beta 0 hat and beta 1 hat. By definition, the 1 entry of cap sig sub beta hat is equal to the variance of beta 0 hat, which is given by sigma squared times the sum of the squared x values divided by n times s sub xx. Similarly, the 2 entry of cap sig sub beta hat is equal to the variance of beta 1 hat, which is equal to sigma squared over s sub xx. Because a covariance matrix is symmetric, the 1 entry and the 2 entry of cap sig sub beta hat are the same, which is the covariance of beta 0 hat and beta 1 hat. It was shown in a previous lecture that the covariance of beta 0 hat and beta 1 hat is given by the expression negative of x bar over s sub xx times sigma squared. Now again, remember, don't forget that negative sign in front. Now putting all these results together, the covariance matrix of the random vector beta hat is therefore given by this 2x2 matrix. And you can see here that we've expressed it two ways. In the second form, we've pulled out sigma squared over s sub xx. Next, let's look at the correlation matrix of the joint distribution of beta 0 hat and beta 1 hat. Let bold R sub beta hat denote the 2x2 correlation matrix associated with the joint distribution of the vector of least squares estimators. The 1 entry of bold R sub beta hat is equal to the correlation of beta 0 hat with itself, and that in turn is equal to the variance of the standardized version of beta 0 hat, which is equal to 1. Similarly, the 2 entry of R sub beta hat is equal to the correlation of beta 1 hat with itself, and that in turn is equal to the variance of the standardized version of beta 1 hat, which again is equal to 1. Like the covariance matrix, the correlation matrix is symmetric, which implies that the 1 entry and the 2 entry of bold R sub beta hat are the same value, and this is the correlation of beta 0 hat and beta 1 hat. In a previous lecture, it was shown that the correlation of beta 0 hat and beta 1 hat is given by the following expression: the negative of x bar divided by the square root of 1 over n times the sum of the squared x values. So putting all these results together, we can construct the correlation matrix of the joint distribution of beta 0 hat and beta 1 hat, and it looks like this. Finally, we can find the functional form of the joint distribution of beta 0 hat and beta 1 hat. Denote by F the PDF of the joint distribution of beta 0 hat and beta 1 hat. If the model error terms are normally distributed, then the joint distribution of the least squares estimators beta 0 hat and beta 1 hat is the bivariate normal distribution, with PDF given as shown here. So this is a function of the least squares estimators beta 0 hat and beta 1 hat, and it's equal to 1 over 2 times pi times 1 over the square root of sigma squared sub beta 0 hat times sigma squared sub beta 1 hat times 1 minus rho squared, all of that times the exponential function evaluated at negative 1/2 times q, where q is the expression shown at the bottom of the slide, and rho is the correlation of beta 0 hat and beta 1 hat. Now this can be expressed also in using matrix notation in the following way. So again, f, which is a function of the least squares estimators beta 0 hat and beta 1 hat, that's equal to 1 over 2 times pi times the square root of the determinant of the covariance matrix of the least squares estimators times the exponential function evaluated at the quadratic form negative 1/2 times the transpose of beta hat minus beta times the inverse of the covariance matrix times beta hat minus beta. So we've seen in this lecture video that when the model error terms are normally distributed, the least squares estimators are normally distributed as well. This allows us to identify the exact sampling distribution of the least squares estimators, and it provides a way to calculate precise, accurate probabilities of events involving those estimators. So that's what I wanted to cover in this lecture video. I'll see you in the next lecture video.